Hi, and welcome to Math 232, section 3.3, geometrical transformations. So here what we're going to do is we're going to take a different view of the matrix, and we're going to see a matrix as operating on a vector to perform some sort of geometrical operation. Okay, so just one word that this has come up again, but just as a reminder, what is an orthonormal basis? So that's a basis where all the vectors are orthogonal and they are all of length 1. Okay, so what we're going to do, and the textbook is a little bit different in this regard, we are going to stick with the 2 dimensions. So we'll be considering always 2 by 2 matrices, and we're going to be considering vectors and what happens to them in R2. Clearly, we can do this in R3, but it's much more complicated. It's more difficult to draw, and so we're going to just omit the geometrical transformations in R3. Okay, so we saw a couple of these things just towards the tail end of the last lecture. And so this one will be a bit of a review, but what we can do is we can rotate a vector about the origin. Let's just see what that looks like. We take some vector v1, there it is, and we decide to rotate it a certain amount, theta, an angle, and we get it moves over to there. Okay, so we take v1, we rotate it, and it ends up somewhere a little bit different. So what we have to do before we try to find a matrix transformation for this is we have to establish that this is linear. I want you to do that as an exercise. It is. So if first you establish this is a linear operation. This is in the textbook, and also, yeah, it's something that you should know how to do. Okay, so you write out what this transformation is, then you apply the linearity conditions and make sure it's linear. Okay, so once we've established it's linear, it is, trust me, proof by intimidation. We are then going to compute the standard matrices. We're going to compute the matrix, and we're going to use this idea of how to compute the matrix for the operation in each one of these exercises that follows. So we're going to compute the matrix, and we're going to do that by considering what happens to the standard basis vectors. Okay, so what I'm basically going to do is see what happens to the standard basis vectors when I rotate them by theta. And then I'm basically considering any vector v as a linear combination of the standard basis vectors. That's a true statement. So then I can just apply the matrix to the vector whose columns are what happens to the standard basis vectors. Okay, let's see how that happens with an example. So what we're doing is we're thinking, okay, we want to get this general problem, but what we're going to first do is we're going to take the vector 1, 0, and we're going to imagine rotating that by theta, and then we're going to be able to easily figure out where that thing is. Okay, so we just going to drop a thing here, and we're going to notice that this distance here is cosine theta, and then this distance here is sine theta. Okay, so that allows us to easily say what the terminal point of the rotated vector is. So we'll write that in this manner: r of rotating by theta, rotating the vector 1, 0, we get out the vector cos theta, sine theta. Okay, we do the same thing. We imagine then now rotating the vector that is this guy here, 0, 1. We rotate it by theta like that. And then we ask what are the coordinates of this point? So we have to look and see what is that and what is that. Okay, so this here is this one here is cos theta again. And then this guy here is minus sine theta. Okay. So make sure that you can rotate either one of those vectors and figure out what the components of the rotated vector is. Confirm that I've done this right. I'm saying that if I rotate 0, 1, I get the vector minus sine theta, cosine theta. Now, immediately once I've done this, I can form the matrix for rotation. So the matrix for the rotation operator by an angle of theta in R2 is this guy here, cos theta, sine theta, minus sine theta, and cos theta. Okay, so now if I want to rotate any vector by some number theta, I simply put that number theta in here by some angle theta, and then I take this matrix and I multiply it onto the vector, and that the vector will rotate by that amount. Okay, so we saw that in section 2.3. Here it is again. Possibly a good idea to stop the video and make sure that you can generate this matrix via drawing yourself a picture and seeing how the standard basis vectors rotate in R2. Okay, so that is that one. Now what we're going to do is consider a few other type of geometric operations. Stretching. So we can stretch in the X or Y direction. Let's just look what stretching looks in the X direction. We have some vector. Let's just draw it here. Here it is. It has a terminal point X, Y. And then we decide to stretch it in the X direction, which means we stretch the X over here like that, and it ends up over here somewhere like that. So it becomes T times X, and the Y coordinate doesn't change. So we're stretching in the X direction. So we're going to do exactly the same thing. To figure out what matrix will do this to our vector, let's again call this V1, and let's figure out now our new vector. We'll call it, I don't know, let's call it V. Well, I didn't call that. Okay, I'll call it V1, and then I'll call this one V1 prime. Okay, so V1 prime is the stretched version of V1, and we want to figure out what matrix would I multiply V by so that I would get V1 prime. So I'm going to say to stretch by some amount, let's call this even TX. We're stretching in the X direction. So I'm going to say to stretch in the X direction, when I stretch the vector 1, 0, what does that mean? Well, clearly, if I'm thinking here of this guy here, 1, 0, when I stretch in the X direction, I simply multiply that 1 by the amount of the stretch, and nothing happens to the Y component. Okay, I similarly do the same thing with the other standard basis vector in R2, and when I stretch here, I'm not changing the Y, I'm only stretching in the X direction. So the X direction, the vector in the X direction, when I'm here, now I'm doing this one, 1, 0, sorry, that's a 0, 1. Let's try that again, 0, 1. When I multiply 0 by my stretching factor, it stays 0, and I'm not stretching in the Y direction. Okay, so that is there. So now I can write this out as a matrix. A stretching matrix by a parameter T in the X direction looks like this. There it is. Okay, try it out. Like let's just assume that TX is, I don't know, 5. We're going to stretch by 5 in the X direction. So let's just take some vector 3 minus 2 and perform this multiplication. We see that we get the vector 15 minus 2. The X component was stretched by 3 and the Y component was left alone. Sorry, the X component was stretched by 5 and the Y component was left alone. Stretching in the X direction. Stretching in the Y direction. Okay, that looks like this. Good time to stop the video. Say, hey, I'm going to do the same thing. This is going to be in the other direction. Can I write out what this is for the basis vectors? And then can I properly put those things into a matrix so I get the proper matrix, and can I check it? Stop the video, do it yourself. Way better than watching me. Okay, so now we're going to take a vector here. Let's just call that V2. It has terminal points, some X and Y. And we're going to stretch it in the Y direction, means you go like this. So the X component won't change. And then the Y component will change by some factor TY times Y. So this is a stretch in the Y direction by TY. Do exactly the same thing. Figure out what TY, the stretch with an amount T in the Y direction, does to the standard basis vectors. Doesn't do anything to the X component. It stretches the Y component. That's what it does. Okay, so now I can quickly write out the matrix. I'm using the same procedure each time. What happens to the basis vectors? Put them in as columns. What happens to the basis vectors? put them in by column. What happens to the standard basis vectors? Put them in as columns. This is my third time, and we're only a few minutes into this lecture, my third time doing this. Okay, it's clearly an important technique. Okay, here it is, 1, 0, 0, ty. Write yourself an example. Make sure that that is stretching in the y direction. Okay, if we want to stretch in both directions, both, we could stretch first in the x direction and then stretch in the y direction. Okay, so this one would be happening first, this one would be happening second. It turns out in this case, it doesn't actually matter, but we are always cognizant of the fact that matrix multiplication is not commutative. Okay, so that we do this multiplication and you see you get a matrix that looks like this. So this matrix will stretch by a certain amount in the y direction and by a different amount in the x direction. If you have the case where these two parameters are the same value, then this is called a dilation when it gets bigger. That's if ty is greater than 1. If it's equal to 1, nothing happens. It's a dilation, or it's called a contraction. It gets smaller. That's if ty is less than 1. Okay. All right, so we have now the ability to use a matrix to rotate a vector, and we also have the ability to use a matrix to cause a vector to be stretched in either the x, y, or both directions. Okay, there's another type of geometrical operation called shear. I'm just going to define this by what it does to the basis vectors. So we'll start out, there's two possible shears. There's horizontal shear. There's horizontal shear, and what that does is it does nothing there, and it does this to the other. Okay, let's see what that looks like. It looks like this as a matrix. Okay, notice how this is different from stretching. Okay, we have a non-zero entity right there. So this is actually taking the first component and of a vector and adding s times the second component. What does this look like? Sorry a sec, my phone is making noise. I'm turning it off. Sorry about that. Okay, what does this look like? We take a vector. Let's just take an actual numeric example. Let's let s equal to 3. So then what we're thinking is doing a horizontal shear of 3. This will then be 1, 3, 0, 1. Okay, and we'll take a vector. Let's take a vector here, 1, 2. So we get the vector here, 1, 2, 1, 2. There it is. Okay, so let's take this vector and multiply it by this matrix and see what we get. We get 1 plus 6, we get 7, and we get 2. Okay, so what's happened? The y component has not changed, and the x component has gotten bigger. So we move over here to see where this is. This is 7 and then 2. So we've moved it to over here like that. Okay, that vector has moved over to there. And that is a horizontal shear. And what you want to be thinking about is you can imagine a box like this. Okay. And you consider all the vectors in that box, like all these vectors, like just imagine all the vectors there. And then you apply that matrix, the horizontal shear, to that matrix, and you end up with a parallelogram. That's a horizontal shear. So all those vectors moved over will become not a straight line. That will become all of those vectors. That is a horizontal shear, and we can use that to see that to provide, if we're thinking of all those vectors together that make up that square, we can then think of that as a solid object, and so this becomes then a deformation of a solid. Okay, so that's the horizontal shear. I'm going to ask you guys to do the vertical shear exercise. Do the vertical shear. Okay, same thing. It'll look similar, but of course the entries will be slightly different. So try that out. That's something you want to be able to do, and it'll also indicate whether you've understood what shear is. Okay, next thing we can do is we can use a matrix to reflect a vector across one or the other of the axes. So either across the x-axis or across the y-axis. So let's just get a picture of what that's looking like. We take a vector, there it is, x, and we reflect it across the x-axis. And so the image of it becomes this guy here. This is, let's see, let's just call this x prime. That is the reflection of x across the x-axis. For that to be a reflection, these angles have to be the same. Okay, so let's just think about what this looks like. We're taking our function and we're taking, say, let me call this x1 and this x2, the axes. I'm taking some number, x1, some vector, x1, x2. And what am I doing when I reflect it across the x-axis? I leave the x component alone and I take the negative of the y component. Once I figure this out, what's actually happening, that is what a reflection is, then this whole problem of finding the matrix becomes really easy, because we're going to do exactly what we did the last 3 times. We're going to see, okay, what happens to the vector 1, 0. I can just follow the rule I've established here. It stays 1, 0. What happens to the vector when I reflect across the x-axis to the vector 0, 1? It becomes, well, let me follow my rule here, 0, minus 1. I will then put those two things into the matrix as columns, 1, 0, 0, minus 1. So that right here is the matrix to reflect any vector that I choose across the x-axis. So for example, should I take the vector v1 is equal to 3, 4, and then I take 1, 0, 0, minus 1, I multiply it by 3, 4, I get the vector 3 minus 4. Okay, you can plot those two things and you'll see that one is above the x-axis and that's reflected, and that is at the right angle, and it's below. Same thing for, we'll do exactly the same thing for vertical reflection. We take an arbitrary vector, there it is, we'll call it x again, and we're going to reflect it across the y-axis, getting this guy here, x prime. Okay, so we're going to reflect it across, let's be consistent, I'll call it the x2 axis. So this angle, theta, is the same as this angle here. We're pretending that the x2 axis is a mirror and we're reflecting it across. What does that function look like? It looks like this. I establish what that transformation looks like, and then I can perform that transformation on the basis vectors. Now this is, I think, the 4th or 5th time I've done this, so I will do that. I will say that fy of 1, 0. I'm going to follow my little rule, and my little rule says take the negative of the first one and write the second one out, and then I will follow my rule on the second standard basis vector, and my rule says take the negative of the first one and leave the second one alone. Okay. I put them into the matrix as columns. Okay. So there is the 2x2 matrix that performs the operation of reflecting vectors across the y-axis. Okay, here comes the complicated one, reflecting across a line through the origin. This is more complicated to see. I'm gonna draw a picture and then I'm gonna do an example. Okay, so because I'm going to use a particular example, I'm gonna draw a particular line. So let me just draw a line. I'm gonna draw this line, x1 plus 3x2 equals 0. What line is that? That one is 3x2 is equal to minus x1, x2 is equal to minus 1/3 x1. Okay, so it's a line with a negative slope. Let's see, and when x1 is say when x1 is minus 3, that's minus 3. X2 will be 1. So it is, this point is on the line, this point is on the line. That allows me to draw my line. Okay, there it is. That's a straight line. And I am now going to reflect across this line. Okay, so this is the line to reflect over. Okay, so how do I go about doing this? Well, I'm going to just take a look at what happens. I'm going to take a vector. Here it is, A. And I'm going to reflect that vector across this line. So I'm going to have to go, it's going to be somewhere around here. This is also got to be theta. And so here, over here is my reflection. There. So I've taken A, I've reflected it across the axis. Now here is what we need to see. We've got this line, we've got this thing reflected across. I'm going to add a line right here. I want that to be in a different color, actually. It's an important line. I'm adding that line right there. Okay, now let's ask ourselves, what is this thing right? Say, maybe there's two things I want to identify, this guy and this guy. Let's start with this guy here, because we've already seen this. Well, we've actually already seen both of them, but we've already seen this right here. That is what? Think about what that is. That is the projection of A onto the line. Projection of A onto L. I'm calling this guy L. So that's the projection. And then what is this? This is the perpendicular. We call this perp of A L, like that. That's the perpendicular component, where we have that the projection of A plus the perpendicular component of A to L equal A itself. Okay, so when I'm thinking of the perpendicular, what is actually this actually also is the projection of A onto the normal line. Okay, so I mean the normal line, let me change colors here. The normal line. So I've got a vector L, and I want to establish the normal. So the normal is this is N. That is perpendicular. So I mean this I could draw it here too. It's not too perpendicular looking, is it? That has to be parallel. Try to make a better job of that so it's more obvious. Okay, so those two things are parallel. Those two green lines are parallel. That is the perpendicular vector to the line L. Now I imagine projecting A onto that green thing. That's exactly the perpendicular component left after I project A onto L itself. Okay, so make sure you can understand why that is a true statement, and notice that N is being defined this way. The dot product of N and L are 0. They are perpendicular to one another. This is really all I need to know. If I understand this drawing, I can go ahead and do one of these. Go ahead and do this problem. I'm going to now try to reflect a arbitrary vector over this line. Okay, so the line, we have a line here. It is this line here, x1 plus 3x2 is equal to 0. I'm going to write that line in its vector format. looks like this. Make sure you can do this. There's the line in this vector format. Now, once I see the line in this vector format, it's very easy for me to write out what the normal of that line is. The normal of the line is some other parameter, 1, 3. Okay, S, like, let's just be clear here. T and S are scalars. So now I have the normal of the line, and I have the, so this is the line, and this is, we're reflecting over. And this is the normal, the perpendicular line to the line we're reflecting over, normal to L. Okay. Let's take a look at what we're trying to figure out on our drawing. We are trying to figure out what this guy is right here. Right? But look at what that guy is, considering this distance right here. What is that distance? Well, we've identified what it is. At least we've identified what half of it is. Half of it is this guy right here. So I am saying that this long black line here is 2 times this long black line, considering the whole thing, is 2 times the projection of A onto N. Now I have a triangle for which I know 2 of the vectors, and I want to find the third one. So then my thing is to say to you here, what I've called A prime, which I'm now going to rewrite this way: the reflection of A over L is A minus 2 times the projection onto N of A. There's my I haven't actually, I mean, I've got N and L exactly, and I've got all that here. Okay, so now I want to find the matrix in order to do this. So I'm just going to consider A is a vector. I'm not going to specify exactly what vector it is. I'm going to now take A to be the 2 standard basis vectors so that I can form the matrix. So I imagine taking, I mean, this is really the only thing that I need to figure out. What I'm going to do is take the projection onto N, onto my normal line of 1, 0. We know how to do this. That is 1, 0 dot 1, 3. That is N, 1, 3. Divided by the norm of 1, 3 squared times 1, 3. And I make that calculation, and I get 1/10, 3/10. I do the same thing, the projection onto N of 0, 1, and I get 0, 1 dot 1, 3. A bunch of these calculations are exactly the same. Okay, I make that calculation. Check my calculations. I got 3/10 and 9/10. Okay, so I'm now going to multiply that by 2. So I'm computing this thing right here. I have not specified A. I'm getting the matrix to do that. So I'm going to take. Actually, I'm going to be possibly a bit clearer here. Really, what I'm going to do is I'm going to go like this. I'm going to take the matrix I don't need to put that in that notation. The matrix I'm going to subtract 2 times the matrix that is the projection onto N of a random vector A. And I'm going to then have that available, and I'm going to be able to multiply that by A. So then I can project any vector that I want. I am trying to find the projection matrix of any vector A across the line x1 plus 3x2. We're almost done. I'm going to take I already know what I is. There's I minus 2 times my projection matrix looks like this: 1/10, 3/10. Where did that come from? That is this thing here, right? What happens to the first basis vector? And then I'm going to put in what happens to the second basis vector. Is this guy here. Like that. I'm going to perform this operation. And if I don't make an arithmetic mistake, I got here 8/10 minus 6/10 minus 6/10 and minus 8/10. There. Okay, what do I have? What I have right here is a matrix. And if I want to reflect any vector across this matrix, if I want to reflect any vector, across the line, x1 plus 3x2 equals 0, I simply take the vector and multiply it by this matrix. Okay, and then I can reflect as many times as I want once I've figured this guy out. Okay, the key to seeing how reflecting across a line works is seeing how the reflection can be seen in terms of projection. So my strong recommendation to you is to basically try to neaten up this discussion that I've done while explaining this. Like, start from scratch, say, okay, how do I figure out what this matrix is for this line? Start with that, clear your paper and draw your picture and go through it methodically like that, and then see that you can generate this matrix, because that's what you need then to be able to do those reflections. Okay, take some time to see this one. This is the hardest. This reflection across a line, which is not one of the two axes, is more difficult to get at. Okay. Let's make some comments here. This is actually a shorter lecture, I'm thinking, and we just want to make a few comments here. There's 4 things I want to comment on, and that is going to be it. What can matrices do to vectors? Okay, yeah, you're a lonely little vector, and along comes a matrix. What can happen to you? Okay, so matrices can scale. So they can scale, make you bigger or smaller in the X or Y direction, or both. They can reflect. So it can cause you to reflect about an XY axis or perhaps over another line. And there's a rotation. I see a projection. You could see projection as a rotating and scaling, right? You get rotated down to the line that you're being projected onto, and then you get scaled to the right size. Okay. All right, so that's basically what can happen. It's a linear operator. There's not a, like, looking at it geometrically, there isn't anything else. All right, so that's 1, 2. Oh, I should maybe just add here. Of course, if you have a matrix filled with numbers, it can do more than one of these things with the same matrix. Okay, you could have a matrix that scales and rotates at the same time. Okay, though that would be a composition of those 2 matrices. Okay. Okay, some matrices, and then we're going to come back to this later. This is a sort of a bit of a foreshadowing. Some matrices are when I'm thinking of them as a linear transformation. So they're going to be doing something to a vector, are length preserving. Okay, this means that whenever you take a matrix times a vector, the length of the vector does not change. It may rotate or something like that, but the length isn't changing. So let's just see which ones are like that. So it's like, which of these linear transformations are length preserving? I mean, clearly not scaling and clearly not projection. So not scaling. I mean, that's the purpose of that is to change the length. Okay, and not projection, right? Your shadow doesn't have to be the same length as you are. It can be under special circumstances, but generally speaking, your shadow is longer than you or shorter than you. Okay, so in general, projection is not length preserving. Okay, but let's take a look at the ones that are length preserving. For example, rotating. I have a vector here. It maybe has a length. Maybe this has a length here of 2, like that. And I rotate it. So we just rotate it by some amount. There, I rotate it over here like that. And to the best of my drawing ability, which I'm not completely happy with in this one, like that, I've rotated this guy around like that, and I have not changed the length. So this is still of length 2. So rotation preserves length. And similarly with reflection, I think this is fairly obvious. Actually, you have something like that, and you decide to reflect it across the x-axis, and it comes down there like that, and it's a reflection and it doesn't change. Like the say, size of your nose stays the same when you look in the mirror. Okay, so reflection and rotating do not, the length does not change. Okay, let's just take a look at one of these matrices that is length preserving and notice some features about the matrix, because that's really kind of an important feature. So let's take a look at rotating by an angle theta. We just showed last lecture, and in fact, in the beginning of this lecture, that matrix looks like this. You should be able to, you should not be memorizing this, okay? You should be able, if somebody asks you, hey, rotate this, provide a matrix that rotates, you shouldn't say, oh, I forgot how to memorize that. No, you should just say, okay, I got to just quickly draw myself a picture, see what happens to the basis vectors, put them in the matrix, and be able to regenerate this matrix. Okay, so here we are. Okay, let's take a look at the columns. Column 1 looks like this. All right, let's take the dot product of column 1 with column 2. That's going to be first element times first element plus second element times second element. 0. The columns are orthogonal. Okay. Let's take a look at the length. The length of C1 is the square root of cosine squared theta plus sine squared theta, which is equal to 1. I take the square root of 1, I get 1. So it is of unit length. And the same thing happens with C2. Okay? C2 is also of unit length. I have to actually go through that, but it's the same exact calculation. Okay, that means that C1 and C2 form an orthonormal basis for R2. Okay, the two vectors form, they're linearly independent. Check that. I mean, you check that these two columns, you can check this. Check linearly independent. And there's 2 of them, so they form a basis as though they span R2. So they're a basis for R2. So there's an orthonormal basis. Okay, that's something to note. And let's my final point is the elementary row operations seen geometrically. So let's talk about our elementary row operations that we use for Gaussian elimination. Elementary row operations. Okay, let's take a look at the elementary row operation that multiplies a row by a scalar. Okay, multiplies a row by a scalar. What does a matrix look like that multiplies one of the rows of an equation by a scalar? Looks like this. This multiplies row 1 by 2. That's a stretch. So we can see the elementary row operations geometrically. Okay, let's take a look at the next one. What's our another one of our row operations is add S times row 2 to row 1. That looks like this. Take row 1, add S times row 2 to it. That is a horizontal shear. Okay, final row operation. Swap rows 1 and 2. The matrix that swaps 2 rows looks like this. Okay, let me just show you that. I want to convince you of that. Say I'm like that. I want to swap 2 rows. Well, let me make the numbers more different so we can really see it. Okay. Right, swap the 2 rows. So this matrix has the effect on another matrix of swapping the 2 rows. Make yourself an example of these two. Like take this, multiply it by some numbers, see what happens. Multiplies the first row by 2. Okay, same thing here. Make yourself an example, convince yourself about what's happening. So we have our row operations. Here's multiplying by a constant, here's adding a multiple of one row to another, and here's swapping the 2 rows. So this matrix here, geometrically, what does this look like? Well, let's just draw a picture to see what that looks like. We're going to look at, let me just look at what this does to a vector. It exchanges X with Y. That's what, and if I apply that, well, I already did that. I applied it to a matrix, it swaps 2 rows. I apply it to a vector, it interchanges Y and X. So what does that look like? Let's draw a picture here. Let's just take a vector like, I don't know, 1, 2, 3, 4, like that, and 1. Let's take a vector there. There's the vector 4, 1. Let's swap X and Y. That'll get us 1, 4. Okay. There it is. Okay. This is the vector 1, 4. Those are the same length. Sometimes it's hard to draw to scale here. I actually think this thing looks like it needs to be a little bit longer. Let's move that guy up. 1, 4. Okay, these are the same length, right? You can calculate the length. It's 4 squared plus 1 squared square root. Both cases, they're the same length. What is happening here? Think about where else you would swap Y and X and then do something. Perhaps finding the inverse, for example. And geometrically, what did that look like? That is a reflection across the Y equals X axis. So this is reflection across the Y equals X axis. Okay, so we have 3 row operations, and we've just prior been seeing them algebraically, and what's called linear algebra, but it's really important to notice how frequently we say, oh, let's geometrically see what's happening so we can understand what's going on. In particular, in this lecture, think about trying to come up with this matrix here without drawing the picture. I think it's really difficult. Like I think it's such a visual aid to draw that picture and say, oh, I can see what's happening. I can see where the perpendicular vector is. I can see where the projection is. I can see how the vectors are adding together. That allows me then to step through and figure out exactly what computations I should be making. Okay, so I've been emphasizing this as we go along, and I'm going to continue to do so. We want to be seeing what's happening geometrically. And in particular, in this last couple of sections, what we've been doing is rather than seeing our matrices as coefficients in a system of linear equations, now we're seeing a matrix in a different light. We're seeing it as some numbers that we then multiply onto another matrix or onto another vector or onto a vector, and it affects some sort of geometrical transformation for the vector when we do that. Okay, that is all for section 3.3. I'll be back shortly. Thanks, guys. Bye.